A giant star is born in silence, burns through its life at incredible speed, and then reaches a point where even light cannot escape what comes next. In this video, the journey follows a hypernova from the outer layers of a massive star to the final collapse that may leave behind a black hole. The process is powerful, but also deeply precise, shaped by gravity, heat, radiation, and the last stages of nuclear fusion. Stay with the story as each layer of the star reveals what happens before one of the universe's most energetic explosions. Like the video, subscribe to the channel and continue into the quiet science of a giant star becoming a black hole. Far from any finished black hole, the story begins in a wide and cold region of a galaxy, where gas and dust drift through the space between stars. This region is a stellar nursery, a place where new stars may form when matter gathers under gravity. It is not empty, although it appears dark across much of its span. Thin gas fills it, mostly hydrogen, with helium and a smaller share of heavier elements made by older stars. Fine dust grains float through it as well, made of carbon, silicon, oxygen, iron, and icy compounds in very small solid pieces. The cloud remains cold by stellar standards, often only a little above absolute zero, and this coldness matters because cooler gas moves more slowly. When gas moves slowly, gravity can more easily draw it together. The outer setting is broad, dim, and patient, shaped by small motions that may continue for millions of years before one dense region becomes a star. Across the surface of such a cloud, starlight from nearby stars warms some dust grains, while other parts stay shielded in darkness. The cloud does not have a hard edge. It thins gradually into the surrounding interstellar medium, the wider mixture of gas, dust, magnetic fields, and cosmic rays between the stars. Some parts are faint and diffuse, others become darker and more compact, blocking the light of stars behind them. In the densest places, molecules form, including molecular hydrogen, which is hydrogen bound in pairs. This molecular gas is hard to observe directly when it is cold, so astronomers often trace it through other molecules, such as carbon monoxide, and through the dust that glows weakly in infrared and submillimeter light. These observations show that the largest star-forming clouds can stretch across many light years and hold enough material to make many stars at once. A hypernova begins with an unusually massive star, and such a star requires a special beginning. A small, isolated clump rarely holds enough mass to create it. Instead, massive stars usually form inside crowded regions, where many young stars are born together from the same parent cloud. The environment is not violent in the dramatic sense, but it is active. Gravity pulls matter inward wherever density rises above its surroundings. Turbulent motion, meaning irregular movement in the gas, creates knots and filaments. Magnetic fields thread through the cloud and influence how gas slides and gathers. Radiation from young stars can warm and push nearby material. Older stars may send winds or shock waves through the region. These forces do not act as a simple chain. They combine, oppose, and reshape one another while gravity continues to favour the densest places. Within the outer cloud, long filaments of gas can become the main roads of star formation. They are narrow compared with the cloud as a whole, but still vast, stretching for light years. Along these filaments, gravity gathers material into clumps. Some clumps remain modest and form low-mass stars. Others continue to draw in gas from their surroundings. A massive star must grow quickly, because its own radiation becomes strong while it is still forming. The light from the young object presses outward on the nearby gas and dust. This pressure can resist further growth, especially when dust absorbs the light and heats up. Yet observations and models show that massive stars still form because gas can fall inward through disks, streams, and uneven flows. The process is not a smooth sphere closing in from all sides. It is structured, with matter finding paths inward through the surrounding cloud. At this outer stage, the future hypernova star is not yet visible as a clear, bright point in ordinary light. Dust hides much of the young object and its inner surroundings. Infrared light can pass through dust more easily than visible light, so telescopes that observe infrared wavelengths can reveal warm material around young massive stars. Radio observations can trace cold gas and ionized regions, where atoms have lost electrons under strong radiation. The earliest signs are often embedded sources, compact bright regions inside darker clouds, and outflows from young stars pushing into the surrounding gas. The outflows show that material is not simply falling inward. Some matter is also being driven outward along preferred directions, carrying away energy and angular momentum. Angular momentum is the tendency of rotating material to keep rotating, and it affects how gas forms disks rather than falling directly into the center. The forming massive star sits inside a cluster environment, and this matters for its later life. Nearby young stars share the same cloud, and their combined light and winds begin to carve cavities in the gas. The most massive young stars heat their surroundings strongly. Ultraviolet radiation breaks apart molecules and ionizes hydrogen, making glowing regions called H2 regions, where hydrogen is mostly ionized. The written name H2 is a traditional term in astronomy, and it marks gas shaped by young hot stars. Around these regions, expanding bubbles can compress nearby gas. Some compressed gas may form more stars. While other parts are dispersed, the cloud becomes uneven, with bright rims, dark lanes, dense knots, and hollowed pockets. The future hypernova star grows within this larger rearrangement of matter. The mass of the forming star is the central condition for the later event. A hypernova is not a separate kind of star at birth, but an unusually energetic form of stellar death linked to very massive stars, often stars that have lost much of their outer envelope before collapse. The beginning, therefore, depends on a star that forms with enough mass to burn fuel rapidly and build a large core. Exact mass limits are not fixed by one number, because rotation, chemical composition, mass loss, and binary companions can change the path. Observations indicate that many massive stars are born in pairs or multiple systems, and a companion can later remove material or alter rotation. At the outer nursery stage, the full fate is not yet set in detail. What is clear is that the star must gather far more mass than the Sun, placing it among the rare, luminous stars that live briefly by cosmic standards. The chemical composition of the cloud also matters. Astronomers call elements heavier than helium metals, even when they are not metals in everyday language. A cloud with more of these heavy elements forms more dust and allows stronger stellar winds later, because radiation couples well to metal-rich gas. A cloud with fewer heavy elements may allow a massive star to keep more of its mass for longer. This difference can influence whether the star later becomes stripped and compact enough for some kinds of energetic explosions. In the nursery itself, heavy elements also help gas cool by radiating energy away. Cooling allows material to condense, while dust shields inner regions from harsh light. The cloud carries a record of older stellar generations, because every heavy element in it was made before the new star began to form. The outer environment remains much larger than the future star. Even a giant star is tiny compared with the cloud that feeds it. The cloud may span many light years, while the young star and its disk occupy only a minute central region within one dense core. Around it, gas continues to drift, collapse, heat, and disperse. Some material becomes part of the star, some remains in the disk, some is pushed away by radiation and outflows. Some may become planets or smaller objects around other stars in the same cluster. Though near very massive stars, strong radiation can erode disks quickly. The future hypernova comes from this same ordinary cosmic material, arranged by gravity and cooled by dust, then gathered into a body bright enough to alter its surroundings while still young. In this first region, the movement is outwardly calm but physically decisive. The galaxy provides the large reservoir. The molecular cloud supplies cold gas and shielding dust. Filaments and clumps guide the matter inward. Radiation, turbulence, and magnetic fields shape the pace and form of collapse. A rare, dense core gathers enough material to form a massive star, while the cluster around it begins to glow and clear the cloud. Nothing in the outer nursery resembles an explosion yet. The essential condition is accumulation, before any collapse, blast, or black hole. There is a dark cloud with enough mass, cold enough gas, and enough time for gravity to draw a giant star into being. The young massive star eventually clears enough of its surroundings for its exterior to become the main region of attention. The broad nursery remains around it, but the focus now rests on the star itself as a large, bright body whose outer surface releases energy at an extraordinary rate. The surface is not solid. It is a layer of hot gas where light finally escapes into space after moving outward from deeper regions. Astronomers call this visible outer layer the photosphere, meaning the region from which most observed light emerges. In a very massive star, the photosphere can be far larger and far hotter than that of the Sun. It shines blue-white when it is still compact and extremely hot, or it may become larger and cooler in later phases. Its appearance depends on mass, age, rotation, chemical composition, and how much material has already been lost. At this stage, the star is defined by its outer radiance, its luminosity, meaning the total energy it gives off each second is immense because its core produces energy rapidly, and its outer layers allow that energy to stream away. A star with many times the mass of the Sun does not simply burn fuel at a slightly greater pace. Its inner pressure and temperature rise steeply, so nuclear fusion runs much faster. The light created inside takes a long and complicated route outward, being absorbed and re-emitted through dense layers of gas. By the time it reaches the photosphere, it has become the outward glow seen across space. This glow is not only a passive sign of the star's energy, it also pushes on the gas around it, because light carries momentum. In a massive star, this outward push becomes one of the central forces shaping the exterior. The outer atmosphere of the star extends above the photosphere as thinner hot gas. In this region, atoms and ions absorb selected wavelengths of light, creating spectral lines that reveal the star's temperature, composition, and motion. A spectral line is a narrow mark in a star's light caused by atoms or ions absorbing or emitting specific colors. For massive stars, these lines often show that gas is moving outward. The star drives a stellar wind, a steady flow of material leaving the surface and escaping into space. This wind is powered by radiation pressure, especially when light interacts with metal ions in the outer atmosphere. The gas does not leave as a gentle breeze in everyday terms. It can travel at hundreds or thousands of kilometers per second, though it is thin compared with the air on Earth. Over time, even a thin wind removes a large amount of mass. The wind changes the star's surroundings and slowly changes the star itself. Near the surface, the outflow begins as hot plasma, which is gas made of charged particles. Electrons and atomic nuclei move under the combined effects of radiation, gravity, pressure, and magnetic fields. Gravity pulls the gas inward, radiation pushes it outward. Where the outward force becomes strong enough, material accelerates away. The rate of mass loss depends strongly on the star's luminosity and metal content. In a metal-rich star, many ions absorb light effectively, so the wind can be stronger. In a metal-poor star, the wind may be weaker, allowing the star to keep more of its mass. These differences matter over the star's life, but in the present outer region, the important fact is that the surface is already losing matter into space. The exterior also rotates if the star formed with angular momentum. Massive stars often rotate rapidly, though not all at the same speed. Rotation makes the star slightly flattened, with the equator wider than the poles. It can mix material between layers and change how mass leaves the surface. In some cases, rotation helps move chemical products from deeper regions closer to the outside, where they can affect the observed spectrum. The outer gas does not behave as a rigid shell. It circulates, vibrates, expands, and contracts under internal waves and pressure changes. Some massive stars show surface variability, with changes in brightness or line shapes that reveal motion in the atmosphere and wind. These changes are not signs of immediate destruction. They are part of the restless balance of a very luminous star. The star's exterior must hold itself against two competing tendencies. Gravity pulls every layer inward. Gas pressure and radiation pressure push outward. Gas pressure comes from the motion of particles, while radiation pressure comes from light itself. In very massive stars, radiation pressure becomes especially important. The more luminous the star, the closer it can approach a limit where outward radiation nearly balances gravity in the outer layers. This is often described through the Eddington limit, a theoretical brightness at which radiation pressure can overcome gravity for certain material. Real stars are more complex than the simple limit, because opacity, composition, rotation, and uneven structure matter. Still, the idea helps explain why the most massive stars have powerful winds and unstable outer envelopes. Their light is strong enough to loosen their own surfaces. The outer layers are mostly hydrogen early in the star's life. Hydrogen is the simplest element, with one proton in its nucleus, and it makes up most ordinary stellar gas at birth. Helium is also abundant, with heavier elements present in smaller amounts. At the surface, the gas remains hot enough that many atoms are ionized. The star's ultraviolet radiation floods the surrounding space, stripping electrons from nearby hydrogen and creating glowing ionized gas. The star also creates a wind-blown bubble as its outflow pushes into the surrounding material. Inside this bubble, gas is hot and thin. Around it, swept-up material may collect in a shell. The outer surface of the star therefore connects directly to its local environment, feeding energy and matter outward while light carves the nearby cloud. The brightness of the massive star gives it a short life. A small star spends its fuel slowly because its core is less compressed and cooler. A massive star has more fuel, but it uses that fuel so rapidly that its lifetime may be only a few million years. From the outside, it can seem steady during much of this time, shining with a strong blue or blue-white light. The surface hides the deep changes taking place below, yet it reveals the pace through its high temperature, strong wind, and intense radiation. The star's outer region is therefore both a cover and a messenger. It does not show the inner structure directly, but it shows that the object is large, hot, luminous, and losing mass. Some massive stars remain within binary systems, where a companion star orbits nearby. From the exterior view, a companion can influence the outer layers through tides, mass transfer, or shared winds. In close systems, gas may be pulled away from one star toward the other if the star expands enough to fill the region where its gravity dominates. This region is called the Roche lobe. At the outer stage, such interaction may begin at the surface and surrounding gas, changing the envelope before deeper layers are exposed. Many massive stars are observed in binaries, so this path is common in nature. A single star can also lose mass through its own wind, but a companion provides another route for removing the outer layers. The star's exterior remains the first clear sign of the path toward an extreme end. It is not yet a compact remnant, and it is not yet an explosion. It is a vast, luminous surface pushing energy into space. Its light presses outward. Its wind carries mass away. Its ultraviolet radiation shapes the gas around it. Its rotation and possible companion disturb the symmetry of its outer layers. The region is still outside the deeper shells, yet it already begins the slow removal of material that can determine the later form of the star. In this outer surface and wind, the future event receives its first visible outline, written not as a sudden blast, but as long, steady loss from a giant star whose own light is strong enough to thin its body. The outer hydrogen layers of the massive star become the next region in the path inward. These layers form the broad envelope that once surrounded the hotter and more processed material below. Hydrogen remains the lightest and most abundant element in the star's original makeup, and in many massive stars it begins as a deep surrounding mantle. Over time, this envelope may be reduced, loosened, or almost completely removed. The process is called stripping, meaning the loss of outer material until deeper layers become exposed. It can happen through the star's own wind, through expansion and instability, through interaction with a companion star, or through a combination of these paths. The result is not a simple peeling away in one moment. It is a long change in which the star's visible identity shifts as the outer hydrogen covering grows thinner. The hydrogen envelope is important because it affects the size, color, wind, and final explosion of the star. When a massive star keeps a large hydrogen envelope, it may expand into a supergiant with a wide, cooler surface. When it loses much of that envelope, it becomes more compact and hotter at the surface, allowing deeper material to influence the light that escapes. Many hypernova models involve stars that have lost most or all of their hydrogen envelope before the final collapse. Observations of some energetic supernova show little or no hydrogen in their spectra, meaning the exploding star was already stripped before death. This does not mean every stripped star makes a hypernova. It means stripping is one key condition that can allow a compact, massive core to produce a very energetic event. In a single massive star, the outer envelope can be removed by radiation-driven winds. The same light that leaves the photosphere also pushes on the upper gas. Ions of heavier elements absorb parts of the radiation, and the absorbed energy helps accelerate gas outward. Across thousands or millions of years, this loss can become substantial. The most luminous stars may lose mass at rates far above the sun's gentle solar wind. The exact rate is uncertain in many cases. Because winds are clumpy rather than perfectly smooth, a clumpy wind can make mass loss appear stronger or weaker depending on how it is measured. Still, the broad result is clear. Very massive stars can shed large amounts of material before their cores reach the end of nuclear burning. Some stars pass through stages of especially strong mass loss. Luminous blue variables are unstable, very bright, massive stars that can show large changes in brightness and powerful outflows. The name describes an observed type of star rather than one single fixed phase for every massive star. During such episodes, the star may eject shells of gas into the surrounding space. These shells expand outward and become part of the circumstellar material, meaning material around the star that came from the star itself. The envelope grows thinner while the local environment becomes richer in the star's lost gas. This gas may contain hydrogen if it came from the original outer layers, and it may also contain helium and nitrogen if deeper or mixed material has reached the surface. The outer region therefore records the star's history in the composition and motion of its expelled shells. A close companion can remove hydrogen even more efficiently. If the massive star expands until its outer gas reaches the region where gravity can flow toward the companion, mass transfer begins. Gas may stream from the larger star toward the smaller companion or into a shared surrounding structure. In some systems, the companion gains mass. In others, much of the gas escapes the pair. The stripped star left behind can be much smaller in radius than before, even though its core remains massive and hot. Binary stripping helps explain why many hydrogen-poor supernovae occur from stars that may not have had winds strong enough to remove the envelope alone. It is especially important because observations indicate that massive stars commonly have companions close enough to influence their lives. As the hydrogen envelope is reduced, the surface spectrum changes. Spectra are spread out starlight, separated by wavelength, and they reveal which elements are present in the outer gas. A hydrogen-rich star shows strong hydrogen features. A stripped star may show weaker hydrogen and stronger helium, nitrogen, carbon, or oxygen features, depending on how deeply the stripping has reached and how much internal mixing has occurred. Stars with powerful winds and exposed processed layers are often classified as Wolf-Rayet stars. These are hot, luminous stars with broad emission lines produced in dense, fast winds. Some Wolf-Rayet stars show helium at the surface, others show carbon and oxygen from deeper layers. The classification reflects what the exterior reveals after outer material has been removed. The shrinking of the hydrogen envelope also changes how radiation escapes. A large hydrogen-rich envelope can absorb and spread energy over a broad volume. A compact stripped star holds less outer mass above the core. If it later explodes, the blast moves through a smaller radius and less hydrogen-rich material. This affects the observed light curve, which is the rise and fading of brightness over time. Hydrogen-rich explosions often show signatures of extended envelopes. Hydrogen-poor explosions are usually more compact and can evolve differently. The most energetic stripped explosions, often linked with broad spectral lines and in some cases gamma-ray bursts, require conditions beyond stripping alone. Yet the lack of a large hydrogen envelope allows fast inner material to escape more directly into space. The removed hydrogen does not vanish. It surrounds the star in layers, arcs, shells, or uneven clouds. Some of it spreads far away under the force of earlier winds. Some remains closer if ejected more recently or slowed by surrounding gas. The shape of this material depends on wind speed, rotation, binary motion, magnetic fields, and the density of the local environment. Fast winds can overtake slower winds, creating compressed shells. A companion can shape the outflow into spirals or uneven structures. The surrounding gas may be smooth in one direction and dense in another. When astronomers observe the regions around massive evolved stars, they often see nebulae that hold a record of repeated loss. These structures belong to the outer history of the star, outside the deeper layers but still connected to them. Stripping also alters the star's future by changing its mass and rotation. Losing mass can carry away angular momentum, slowing the star's spin. A companion can either remove angular momentum or transfer it, depending on the details of the orbit and mass flow. Rotation matters because it can mix chemical elements and influence the shape of later collapse. For some hypernova and gamma-ray burst models, a rapidly rotating core is important. However, it remains difficult to know how much rotation the deep core keeps after the outer layers are lost. Observations show surface rotation and binary properties, while the inner rotation is harder to measure. The known point is that outer stripping is tied to the movement of both mass and angular momentum, and these changes help shape what the star can become. The boundary between the remaining surface and the lost envelope is not a clean solid line. The star is gas throughout, and its outer composition changes gradually, or through layers shaped by mixing. As hydrogen thins, helium-rich material may lie closer to the visible surface. The star becomes hotter and more compact because the swollen outer covering no longer dominates its size. Its wind may become faster and its radiation harder, with more ultraviolet light. The surrounding gas may glow under this radiation, while the star itself appears as a compact source with strong emission features. This region is still outside the deeper burning shells, but it marks a major inward step. The original birth covering no longer hides the processed material beneath as completely as before. In this stripped outer region, the future hypernova becomes more physically possible, though not guaranteed. The star has moved from a broad hydrogen-rich giant toward a more exposed massive core. Its winds have carried matter into space. A companion may have pulled away gas that the star could not remove alone. Spectral signs show the changing surface composition. The local environment holds shells and streams of discarded material. The star is becoming bare in the astronomical sense, with its first envelope reduced and its deeper layers brought closer to view. The inward path has left the cold nursery and the bright exterior behind, and it now rests on the loss of hydrogen, where the outer covering thins and the star begins to reveal the material that was once hidden below. Beneath the stripped hydrogen covering, the helium-rich shell becomes the next region of the star. Helium is the second simplest element, with 2 protons in its nucleus, and it forms both from the star's original birth material and from hydrogen fusion during the star's earlier life. In a massive star that has lost much of its outer hydrogen, helium may become visible at or near the surface. It is not a quiet, decorative layer. It is hot, dense, and connected to the star's changing balance. It surrounds heavier inner regions and marks a clear inward step from the original envelope toward the deeper products of nuclear burning. In a stripped, massive star, this shell can form much of the remaining outer body, glowing under intense radiation and feeding a strong wind into space. The helium-rich shell exists because the star has already spent a major part of its life turning hydrogen into helium in its central region. Hydrogen fusion is the process by which hydrogen nuclei combine to form helium, releasing energy. In very massive stars, this process is dominated by a cycle involving carbon, nitrogen, and oxygen as catalysts. These nuclei help hydrogen fuse more quickly at high temperatures. While the net result remains the same, hydrogen becomes helium, and energy supports the star. When hydrogen in the central region is depleted, the structure adjusts. A helium-rich core or inner region remains, while hydrogen may still burn in the surrounding shell if enough hydrogen remains. In a stripped star, much of the hydrogen outside has been removed, so helium becomes the dominant material above the deeper layers. The helium layer is hotter than the lost hydrogen envelope because it lies closer to the star's centre and under greater pressure. Pressure is the force per area produced by the weight and motion of overlying material. In this shell, gravity squeezes the gas more strongly than in the outer envelope, raising temperature and density. The gas is mostly plasma, with electrons separated from nuclei. Light does not move freely in a straight path through it. Photons are absorbed, scattered, and re-emitted many times. Energy moves outward through radiation and sometimes through convection, which is bulk motion of hot gas rising and cooler gas sinking. The exact balance depends on the star's mass, composition, and stage of evolution. The shell is part of a living structure, not a static layer. Helium itself becomes fuel when temperatures rise high enough. Helium fusion joins helium nuclei into carbon and oxygen. The main process is often called the triple alpha process, because 3 helium nuclei, also called alpha particles, combine in steps to form carbon. Some of that carbon can capture another helium nucleus to form oxygen. This burning does not happen easily at low temperature, because helium nuclei carry positive charge and repel one another. The gas must be extremely hot and dense for collisions to overcome this repulsion often enough. In massive stars, helium burning can occur after the main hydrogen burning phase, and it can continue in central regions and later in shells. At the present layer, helium-rich material forms both a fuel zone and a surrounding reservoir shaped by the star's earlier life. The products of helium burning begin to alter the chemical character of the star. Carbon and oxygen appear in greater amounts below and within regions where helium has burned. Nitrogen may also be present near the outer helium-rich layers if material has been processed by hydrogen burning through the carbon, nitrogen, and oxygen cycle. Spectra of stripped massive stars can show different surface compositions depending on how deep the stripping has reached. A star with helium and nitrogen features may be exposing material that has undergone hydrogen burning. A star with strong carbon and oxygen features may be exposing still deeper helium-burning products. The helium shell therefore forms part of a chemical sequence. It is a transition from light original material to heavier products built inside the star. In the outer part of the helium-rich region, the star may be observed as a hot-stripped object with a powerful wind. Wolf-Rayet stars of the nitrogen sequence show helium and nitrogen at the surface, while other types show carbon and oxygen. These categories describe spectra, and they do not always map perfectly onto one simple internal layer, but they help connect observation with structure. The broad emission lines of such stars often come from the wind rather than the photosphere alone. The wind can be dense enough that the usual visible surface is effectively inside moving gas. In that case, the observed exterior is partly a flowing atmosphere. Helium-rich material may be leaving the star continuously, carrying mass and chemical products into the surrounding space. The helium shell also influences the size of the stripped star. Without a large hydrogen envelope, the star can remain compact compared with a red supergiant. Its surface temperature is high, and its radiation is rich in ultraviolet light. The radius may still be several times that of the Sun or more, but it is small compared with the vast swollen envelopes of some massive stars. This compact form matters because the outer layers are closer to the deep energy source and less able to spread a later blast over a huge volume. At the current inward layer, the important point is structural. The star has become more concentrated. Helium-rich gas forms a tight, hot shell around heavier material, instead of lying deeply hidden below a broad hydrogen blanket. The stability of the helium shell depends on the balance between gravity, pressure, radiation, and nuclear energy. When helium burns, It releases energy that helps support surrounding layers. When burning shifts inward or outward, the shell responds. Massive stars do not burn all fuels at once in a uniform body. They build layered structures, with different kinds of fusion active in different zones as the star ages. Helium may burn in one region, while other fuels burn deeper inside. The star's interior resembles a set of shells in the sense of composition and process, though the boundaries are gaseous and may shift. The helium-rich shell is one such region, and its behavior helps determine how the mass is arranged above the core. The timescale of helium burning is shorter than hydrogen burning. A massive star may spend millions of years burning hydrogen, but a shorter span burning helium, often hundreds of thousands of years or less depending on mass. The reason is that each later fuel stage supplies less total support time and occurs under more extreme conditions. The star moves through its advanced life quickly by cosmic standards. From the outside, it may still appear bright and stable for long periods in human terms, but internally the pace has increased. The helium-rich shell is therefore a sign that the star has moved beyond its longest stage. It is still not collapsing, and it is still supported, but its fuel history has shifted inward. Uncertainties remain in the details of this region. Stellar evolution models must include rotation, wind clumping, magnetic effects, mixing, and binary interaction, and each can change the mass and composition of the helium shell. Observations provide surface spectra, luminosities, wind speeds, and sometimes surrounding nebulae. But the interior cannot be directly opened. Astroseismology, the study of stellar vibrations, can reveal internal information for some stars, yet it is difficult for many massive stripped stars. Researchers therefore compare models with observed populations and explosion remnants. The broad consensus remains that helium-rich layers are central to the evolution of stripped massive stars, while the precise amount of helium left before collapse can vary widely. The helium shell also stores the memory of the star's outer loss. If stripping stops with much helium still present, the later explosion may show helium features, depending on mixing and excitation. If stripping continues deeper, helium may be reduced or hidden, and carbon and oxygen may dominate the surface. In some observed stellar explosions, helium is clear. In others, it is weak or absent. The absence of helium lines does not always prove that no helium exists, because helium may require non-thermal excitation from radioactive decay products to appear strongly in spectra. This means the observed signature depends on both composition and energy transport. In the helium-rich region, science must hold both known structure and observational limits together. The inward path through the helium shell is calm in description but intense in physics. The gas is hot, compressed, and chemically changed. It may burn, flow, mix, and escape through winds. It lies beneath the lost hydrogen envelope and above zones richer in carbon and oxygen. It helps define the stripped star as compact and luminous. It marks the place where the star's earlier hydrogen-burning life has left its main product, and where new fusion products begin to appear. The star is becoming less like its birth composition and more like a layered furnace of heavier nuclei. In this helium-rich shell, heat sits beneath the surface, and the star's remaining body grows more concentrated around the deeper regions that continue the inward sequence. Beneath the helium-rich shell, the star reaches the carbon and oxygen zone, where the products of helium burning become the main material. This region is deeper, hotter, and denser than the layers above it. It is no longer shaped mainly by the original hydrogen of the birth cloud, or by the helium that formed during the first long stage of fusion. It is shaped by new nuclei made inside the star. Carbon has 6 protons in its nucleus, and oxygen has 8. These elements are common in the universe partly because many generations of stars make them in large amounts. In a massive star moving toward its final stages, they gather in a broad inner zone that carries the record of helium fusion and prepares the structure for still more advanced burning. The carbon and oxygen zone forms after helium nuclei combine under high temperature and pressure. The triple alpha process builds carbon, and some carbon captures helium to form oxygen. The balance between carbon and oxygen depends on reaction rates, temperature, density, and mixing. This balance is important because it influences how later burning proceeds, but it is not measured directly inside a living massive star. Models estimate it from nuclear physics and from observations of evolved stars and supernova debris. What is clear is that the star has crossed into a region where heavier elements are no longer rare additives. Carbon and oxygen now make up much of the local material, forming a thick chemical layer between the helium shell outside and deeper, more processed regions inside. In this zone, temperature rises high enough for carbon burning to become possible after helium burning has advanced. Carbon burning means carbon nuclei collide and fuse into heavier nuclei, releasing energy and creating products such as neon, sodium, magnesium, and other nearby elements. This stage requires far greater heat than helium burning because carbon nuclei have stronger positive charges and repel each other more strongly. The gas must be squeezed until collisions become energetic enough. In massive stars, the central parts reach these conditions naturally as gravity contracts the inner regions after each fuel source becomes less able to support the star. The carbon and oxygen zone therefore contains both the ashes of one stage and, in its hotter parts, the fuel for another. The structure is not uniform. Some parts of the carbon and oxygen zone may be actively burning carbon, while other parts are made of carbon and oxygen that are not burning strongly at that moment. Layers can be separated by temperature and density, but they remain gaseous and dynamic. Convection may carry material within burning regions, mixing fuel and ash. Radiative zones may transport energy more quietly through repeated absorption and emission of light. In advanced massive stars, neutrinos also become important. A neutrino is a very light particle that escapes from dense stellar matter with little interaction. As temperatures rise, neutrino emission can carry energy out of the core efficiently. This energy loss makes later stages shorter, because the star must burn fuel faster to maintain pressure. The carbon and oxygen zone is hidden from direct sight in the living star. Even if outer stripping exposes deep material at the surface, the interior remains opaque. Astronomers infer its existence from the physics of stellar evolution, from observed surface compositions of stripped stars, and from the elements found after explosions. When a massive star dies and ejects material, oxygen is often one of the clearest signs of the inner layers. Strong oxygen lines in supernova spectra and remnants reveal that large amounts of oxygen were made before collapse. Carbon may also be present, though its signatures can be harder to interpret. The later debris confirms that the quiet inner building of carbon and oxygen is a real and major part of the star's life. Oxygen becomes especially abundant because helium burning can convert carbon onward into oxygen. But not all carbon is consumed. The exact ratio affects the later inner evolution. A higher carbon fraction can change how carbon burning develops, how convection behaves, and how massive the later inner core becomes. Nuclear reaction rates at stellar energies carry uncertainty, especially for the reaction in which carbon captures helium to become oxygen. Laboratory measurements and theory continue to refine these rates. Stellar models therefore include ranges, and scientists compare them with observations. The uncertainty does not remove the main picture. The star builds a carbon and oxygen-rich interior, and that interior becomes the foundation for the next inward chemical layers. The density of this region is far beyond ordinary gas on Earth, though it remains a plasma rather than a solid. Atomic nuclei and electrons move in a compact, energetic mixture. Radiation is trapped for long paths. Pressure rises from particle motion, radiation, and in deeper places from quantum effects involving electrons. Quantum effects become important when matter is compressed so strongly that electrons resist being squeezed into the same states. This resistance is called electron degeneracy pressure, in the carbon and oxygen zone of a massive star before final collapse. Ordinary thermal pressure and radiation still play major roles, but degeneracy can become more relevant in some deeper and later conditions. The star's support is becoming more complex as gravity pushes inward. The carbon and oxygen zone also helps determine the star's final mass arrangement. The size of this zone depends on the original mass of the star, how much mass was lost from the outside, how much mixing occurred, and whether a companion changed the structure. A larger carbon and oxygen core generally points to a more massive evolved star. However, the connection is not simple, because winds and binary stripping can remove outer layers without removing the inner core in the same way. Two stars with different birth masses may sometimes reach similar stripped states, while stars with similar birth masses may end with different core sizes. This is one reason the path to a hypernova is not set by birth mass alone. In the carbon-burning parts, energy generation becomes less steady over long spans than in earlier stages. Hydrogen burning can last for millions of years in a massive star. Helium burning is shorter. Carbon burning is shorter still, often lasting only hundreds or thousands of years in very massive stars, depending on the model. The star remains outwardly luminous, but inside it is moving through fuel stages at an accelerating pace. The reason is partly that later fuels release less energy per unit mass, and partly that neutrino losses become stronger. Much of the energy made deep inside no longer helps brighten the surface. It escapes as neutrinos, leaving the star to contract and heat further. The carbon and oxygen zone is also a region of element making in the plainer sense. Carbon is central to chemistry in planets and living systems, while oxygen is a major part of rocks, water, and planetary atmospheres. In the star, these elements are not gentle or biological. They are hot nuclei in dense plasma, yet their later release into space can enrich future clouds. The same oxygen that may one day become part of silicate dust or water first exists here as the ash of helium fusion. The same carbon that may later form grains or molecules is built in this deep stellar layer. The star is not creating these elements for a purpose. It is following the pressures and temperatures required by its own mass. The boundary above this zone, toward helium-rich material, may be gradual or mixed. The boundary below, toward more advanced burning products, is also not a rigid surface. Massive stars are layered by composition because each fuel burns under different conditions, but convection, rotation, and shell burning can blur or reshape these layers. In some regions, fresh fuel is mixed into hotter zones. In others, ash accumulates. The star's interior becomes a set of nested chemical regions, each one made from the previous one under greater compression. The carbon and oxygen zone is one of the broad and important middle layers in this sequence. In this inward region, the star is no longer defined by what it was born with, it is defined by what it has made. Carbon and oxygen fill a dense layer where helium burning has left its strongest mark, and carbon burning may begin its work. The gas is hidden, hot, and compressed, with energy moving through radiation, convection, and escaping neutrinos. Its details contain uncertainties, especially in reaction rates and mixing, but its role is well established. It is the place where heavier elements form slowly compared with the final collapse, yet quickly compared with the long life of smaller stars. The inward path now rests in a zone of carbon and oxygen, where the giant star's deep chemistry becomes the next quiet step toward its final form. Deeper than the carbon and oxygen zone, the star reaches a region where neon and magnesium become important products of advanced burning. This layer is denser and hotter than the carbon-rich material outside it, and it belongs to a later stage in the star's inward development. Neon has 10 protons in its nucleus, while magnesium has 12. They're heavier than carbon and oxygen, and in a massive star they can be made when carbon burning changes the inner composition. The region is not a smooth storehouse of one element alone. It contains a mixture of nuclei, with neon, magnesium, sodium, oxygen, and other nearby elements present in amounts shaped by the temperature, density, and earlier burning history. It is a place where the star's inner balance grows more demanding, because each new fuel requires harsher conditions than the one before it. The neon and magnesium region forms mainly from the ashes of carbon burning. When carbon nuclei fuse, they can follow several paths. Some reactions create neon and helium. Some create sodium and a proton. Some lead to magnesium and other nuclei through additional captures and decays. The exact mixture depends on the conditions in the burning zone. Once carbon burning has changed the material, a layer rich in oxygen, neon, and magnesium remains in a very massive star. This material lies inside the broader carbon and oxygen zone, and outside regions that will become still more strongly processed. The star is now layered like a sequence of nuclear histories, each deeper layer carrying evidence of stronger compression and higher heat. Neon itself becomes a fuel under extreme conditions, but its burning begins differently from the fusion of lighter nuclei. At very high temperatures, energetic gamma-ray photons can strike neon nuclei and break them apart. This process is called photodisintegration, meaning that high-energy light splits a nucleus. A neon nucleus may release a helium nucleus, leaving oxygen behind. The freed helium nuclei can then be captured by other nuclei, building heavier elements such as magnesium and silicon. In this way, neon burning is tied to both destruction and construction. Light breaks some nuclei apart, and the fragments help build new ones. The process requires temperatures far beyond those of helium or carbon burning, so it occurs only after gravity has compressed the inner star further. The region is held in a careful and temporary balance. Gravity presses inward on all sides, while pressure from hot particles and radiation presses outward. Nuclear reactions supply energy, but the energy does not remain in the star as effectively as it did in earlier stages. Neutrinos carry away an increasing share. Because neutrinos escape so easily, the inner layers cool in a special sense even while their temperature is extremely high. They lose energy without making the surface much brighter. This loss makes the star contract further and burn fuel more quickly. The neon burning stage in a massive star may last only years or less, depending on the mass and model. This is short in stellar terms, yet within the layer it is enough time to alter the composition deeply. Magnesium in this region is both a product and a participant. It can be formed by captures involving helium nuclei, protons, or neutrons, and it can be changed again as temperatures rise. Nuclei in the region do not sit permanently in one form. They react, decay, capture particles, and shift toward mixtures favoured by the conditions around them. Some reactions release energy, others consume energy or redistribute it. The star's interior does not choose a single path. It follows many nuclear channels at once, with some more common than others. Scientists model these channels through nuclear reaction networks, which track how many kinds of nuclei change over time. The broad outcome is a progressive movement from lighter fuels toward heavier, more tightly bound nuclei. The neon and magnesium region remains hidden behind all outer layers. It cannot be seen directly through ordinary light because the overlying star is opaque. Its presence is inferred from stellar models, from the observed lives of massive stars, and from the debris of supernovae and hypernovae after the star is torn open. In remnants, magnesium and neon can appear in hot gas seen through X-ray observations and in spectral lines at other wavelengths. These elements help identify which layers were ejected and how deeply the explosion reached. The pattern is not always simple, because explosion energy, mixing, asymmetry, and fallback can rearrange what becomes visible. Still, the existence of neon and magnesium-rich material inside massive evolved stars is a standard part of stellar evolution. This region also shows how the star changes from long, stable burning toward rapid late-stage adjustment. In the main hydrogen burning stage, the star can maintain a broad equilibrium for millions of years. In helium burning, the timescale becomes shorter. In carbon burning, it shortens further. With neon burning, the remaining time contracts sharply. The reason is not that the star becomes less massive or less luminous in a simple way. It is that the deep core must reach greater temperatures to use each successive fuel, and energy losses through neutrinos become very strong. The star burns faster but gains less long-term support. Its inner structure becomes more compact, and small changes in one layer can alter the pressure and temperature in neighboring layers. The neon and magnesium region may include active shell burning rather than only central burning. In a massive evolved star, nuclear burning can occur in shells around more processed inner material. One shell may burn carbon, while another deeper zone burns neon or oxygen. These shells can be convective, carrying hot material outward and cooler material inward within a limited region. Convection in advanced burning shells can be vigorous, and its interaction with neighboring layers is complex. Some models show that shell boundaries may shift, merge, or entrain small amounts of material from adjacent zones. The details affect the final structure before collapse. It remains uncertain exactly how all such late-stage mixing proceeds in real stars, because the timescales are short and direct observation is difficult. Pressure grows inward in this region not only because of gravity but because the mass above it is large. Even after stripping has removed outer hydrogen, and perhaps much helium, the remaining star still holds a heavy core. Every layer presses on the layers beneath it. The neon and magnesium region carries the weight of the outer processed shells while being squeezed by the deeper core's pull. Matter here is far from ordinary. Electrons move freely through the plasma. Nuclei collide at high energies. Radiation is intense. Neutrinos stream out. The gas has no solid surface, but it has structure through composition, temperature, and motion. Its boundaries are defined by what fuel is present and what reactions dominate. The chemical direction of this layer is inward and upward in mass. Carbon burning has prepared the neon and magnesium mixture. Neon burning can push material toward oxygen, magnesium, and silicon group nuclei. The star is moving closer to nuclei that are more tightly bound. A tightly bound nucleus holds its protons and neutrons with greater binding energy, meaning it is more stable against being pulled apart under ordinary conditions. Fusion releases energy when lighter nuclei combine into more tightly bound ones, but this trend has a limit. At this stage, the star has not reached that limit in the present region. It is still able to gain support from advanced burning, but that support is becoming brief and costly. Rotation and earlier mass loss can influence this layer indirectly. A rotating star can mix chemical products and change the size of its core. Mass loss can change the pressure on inner layers and alter how the star evolves after hydrogen and helium are removed. A companion can strip the outside while leaving the neon and magnesium region to develop within a compact remnant star. These outer histories shape the conditions under which the inner shells form. Still, once the star reaches this depth, the local physics is ruled mainly by extreme heat, density, and nuclear reactions. The earlier outer changes have brought the star to a certain structure, and this layer now responds to the pressure of that structure from within. The neon and magnesium region is therefore a short-lived but important inward stage. It is a region of changed ashes, where carbon has already given way to heavier products, and where high-energy light helps drive further reactions. Its material is compressed beneath the carbon and oxygen zone and above hotter inner shells. Energy is made, lost, and carried through matter that remains hidden until an explosion reveals it. The balance is more urgent than in the outer layers. But it is still a balance. The star has not yet failed. It still resists gravity through pressure and burning, even as each process lasts for a shorter time. In this deeper zone, pressure grows inward, the fuel becomes heavier, and the giant star continues its quiet movement toward the limits of stellar support. Inside the neon and magnesium region, the star reaches the oxygen-burning shell, a deeper layer where oxygen becomes the main fuel under still greater heat and pressure. Oxygen has 8 protons in its nucleus, and it is one of the major products of helium burning in massive stars. In the outer carbon and oxygen zone, oxygen is abundant but not always burning strongly. In this deeper shell, conditions become severe enough for oxygen nuclei to collide and fuse. The process requires extremely high temperature because oxygen nuclei repel one another more strongly than lighter nuclei do. Gravity supplies the compression that raises the temperature, while earlier fuel stages leave behind the oxygen-rich material needed for this burning. The shell is part of the star's inward structure, hidden beneath the layers already formed and shaped by the short, intense, late life of the star. Oxygen burning is not a single neat reaction. When 2 oxygen nuclei collide, several outcomes are possible. The reactions can make silicon, sulfur, phosphorus, magnesium, and other nuclei, along with particles such as protons, neutrons, and helium nuclei. These particles may then be captured by other nuclei and create further changes. The region becomes a busy network of reactions, with matter moving through many nuclear paths at once. Some of these reactions release energy that helps support the shell against gravity. Some redistribute particles and change the balance of elements. The result is a layer that no longer resembles the oxygen-rich material that entered it. It begins to create the group of heavier elements that belong closer to the star's center. The temperature in the oxygen-burning shell is far beyond ordinary experience, rising to billions of degrees Celsius in the deepest massive star models. At such temperatures, atoms cannot exist as neutral atoms. Electrons are separated from nuclei, and the material is a dense plasma. Radiation fills the region with high-energy photons. Neutrinos are produced in large numbers and escape through the star, carrying energy away. This energy loss is one reason oxygen burning is brief. In many massive star models, oxygen burning may last months or years in central regions, while shell burning can occur in shorter or shifting episodes. The exact duration depends on the star's mass, its prior mass loss, its rotation, and its internal mixing. The known pattern is that the star is now moving through fuel stages very quickly, compared with its long hydrogen-burning life. The shell is called a shell because it surrounds deeper, more processed matter, not because it is hard or sharply bounded. It is gaseous, hot, and moving. In some places, oxygen burning can drive convection. Hotter material rises within the shell, cooler material sinks, and the motion mixes fresh fuel with burning products. Convective flow in such an advanced burning shell can be vigorous. It can shape the final composition and may create unevenness in density and temperature. The details are difficult to know exactly, because this activity occurs deep inside the star and shortly before collapse. Computer models show that these late shells can be complex, with motions that are not perfectly spherical. Observations after explosions may carry traces of this structure, but they cannot reveal every motion that occurred before the star died. Energy from oxygen burning helps hold the surrounding layers for a time. The star remains in hydrostatic balance, meaning inward gravity is balanced by outward pressure at each layer, though this balance is changing and temporary. The pressure comes from hot particles, radiation, and the behavior of electrons under compression. Oxygen burning adds heat, but neutrino cooling drains energy quickly. The shell therefore works like a deep furnace that must burn rapidly to maintain support. Its energy does not mainly appear as a sudden brightening at the surface. The outer star may change little in visible light while the inner region passes through this stage. The reason is that photons created deep inside cannot simply stream out at once, and much of the energy leaves as neutrinos that do not brighten the star. The composition produced in the oxygen-burning shell is important for later observations. Silicon, sulfur, argon, calcium, and related elements can be made in advanced burning stages or altered by later explosive burning. When a hypernova or energetic supernova ejects material, these elements may appear in spectra and remnants. Their distribution helps scientists reconstruct the layers that existed before collapse and the strength of the explosion that followed. Oxygen itself is also a major observed element in many stripped envelope explosions. Some oxygen may remain unburned in outer parts, while deeper oxygen is changed into heavier nuclei. The final pattern depends on how much oxygen burning occurred before collapse, and how the explosion processed the layers afterward. This shell also reflects the star's approach toward nuclear limits. Fusion releases energy when lighter nuclei combine into more tightly bound nuclei, but the energy gained becomes less favorable as nuclei grow heavier. Oxygen can still burn and provide support, but the star is moving toward the region where fusion will no longer supply usable energy. Each stage requires higher temperature and gives less time. The oxygen-burning shell sits close to this limit, where the star is still active and supported, but the available path is narrowing. Matter is becoming richer in silicon group elements, which belong to the next inward step in the star's layered structure. The density in this region is high enough for interactions to occur rapidly. Nuclei collide often. Particles released in one reaction can be captured almost immediately by another nucleus. The shell is not chemically calm. It is a constantly changing plasma in which the identities of nuclei are shaped by local conditions. The rates of these reactions come from nuclear physics measured in laboratories and extended through theory to the extreme conditions of stars. Some rates are better known than others. Uncertainties remain, and they affect the predicted abundance of certain elements. Yet the broad role of oxygen burning in massive stars is secure. It is the stage that turns oxygen-rich material into many of the elements between oxygen and the iron group. The oxygen-burning shell is also connected to waves and motion in the star. Late-burning shells can stir the surrounding material and generate internal waves. These waves may carry energy outward, though how much they affect the surface before collapse remains an active area of research. Observations of some massive stars show increased mass loss before explosion, but the causes vary and are not always clear. In the present region, it is enough to say that oxygen burning can be dynamic inside the star. It may not be a silent, smooth ring. It can be turbulent, uneven, and strongly convective, while still remaining buried beneath opaque layers. The pressure above the oxygen-burning shell includes the weight of the carbon and oxygen zone, the neon and magnesium region, and any remaining helium-rich material beyond them. The pressure below comes from deeper material becoming still more compact. The shell exists between these forces, supplying heat to resist collapse locally. If burning becomes stronger, it can expand the shell slightly and reduce temperature. If burning weakens or fuel is depleted, gravity contracts the region and raises temperature again. This self-regulating pattern operates in many stellar burning stages, but in late stages the regulation occurs over shorter times. The star has less time to adjust because neutrino losses are strong and fuel is consumed quickly. As oxygen burning continues, ash accumulates. This ash contains silicon and sulfur among other nuclei. The ash does not remain separate in a perfect layer, because convection and later burning can mix and reshape it. Still, the star develops a deeper concentration of silicon-rich material, while oxygen-rich material remains outside or in partly burned zones. The inward structure becomes more compressed and chemically distinct. Each layer is a record of a different fuel and a different temperature. The oxygen-burning shell records the moment when oxygen itself becomes a source of support and a source of heavier elements. In this region, the giant star remains alive through a deep and brief fire. Oxygen nuclei fuse in dense plasma, creating heavier material and releasing energy that holds gravity back for a limited time. Neutrinos carry much of that energy away, shortening the stage and keeping the surface from showing the full intensity within. The shell may convect, shift, and leave uneven patterns that later become part of the star's final structure. It is not yet the core's failure, and it is not yet the blast. It is the inward furnace where oxygen changes under great pressure, making the next set of elements while the star continues to balance itself in the last active layers before the center becomes dominated by still heavier ash. Deeper than the oxygen-burning shell, the star reaches the silicon-burning layer, the last sustained stage of nuclear fusion before the inner core becomes unable to support itself. This region lies close to the center, where temperature and density are at their highest during the star's life before collapse. Silicon has 14 protons in its nucleus, and it belongs to a group of elements that are closer to the limit where fusion no longer provides useful energy. In this layer, matter is no longer composed mainly of lighter nuclei such as helium, carbon, or oxygen. It is dominated by silicon and related nuclei, along with a shifting mixture of particles produced by intense reactions. The environment is extreme, and the processes are rapid compared with earlier stages. Silicon burning does not proceed as a simple fusion of two silicon nuclei into a heavier element. Instead, it occurs through a complex network of reactions driven by high-energy photons and particle captures. At temperatures of several billion degrees Celsius, gamma-ray photons can break apart nuclei. A process known as photodisintegration. Silicon nuclei can be partially broken into smaller components such as helium nuclei, protons, and neutrons. These particles then interact with other nuclei, building up a distribution of elements around the ion group. The reactions tend toward a state known as nuclear statistical equilibrium, where the relative abundances of nuclei are determined by temperature, density, and nuclear binding energies rather than by one dominant reaction path. In this state, iron group elements, including iron and nickel, become prominent because they are among the most tightly bound nuclei. The silicon burning layer is therefore a region of both destruction and assembly, similar in principle to the neon burning stage but operating at even higher energies and with different outcomes. The repeated breaking and rebuilding of nuclei leads to a composition that approaches a balance among many species. Nickel, especially a form called nickel-56, is often produced in significant amounts in these conditions. Nickel-56 is unstable and later decays into cobalt and then into iron, releasing energy that can power the light from a supernova after the explosion. At the present stage, however, this material remains deep inside the star, part of the dense inner structure that has not yet been exposed. The duration of silicon burning is extremely short in stellar terms. While hydrogen burning may last millions of years, and helium burning hundreds of thousands of years, silicon burning may last only days in the core of a very massive star. In shell form, it may persist for a similarly brief span or occur in shifting regions as the structure adjusts. The reason for this rapid pace lies in the combined effects of high temperature, strong neutrino losses, and the limited energy that can be gained from fusing nuclei near the iron group. The star must burn rapidly to maintain pressure, yet the fuel does not provide long-term support. Neutrinos carry away energy efficiently, further reducing the time available for this stage. The physical conditions in the silicon burning layer are extreme even by stellar standards. The density is very high, and the pressure includes contributions from thermal motion, radiation, and increasingly from electron degeneracy. Electron degeneracy pressure arises when electrons are packed so closely that quantum rules restrict how they can occupy energy states, creating a pressure that does not depend directly on temperature. In the silicon burning region, degeneracy is not yet the sole support, but it begins to play a larger role as the core contracts and heats. The interplay between thermal pressure, radiation pressure, and degeneracy pressure becomes more intricate as the star approaches its final inward transition. Convection can occur in parts of the silicon burning layer, though its extent depends on the exact conditions and models used. If convection is present, it mixes material within the burning region, helping to maintain a steady supply of fuel and distributing the products. This mixing can influence the final composition of the core and the surrounding shells. However, because the timescale is so short, the extent of mixing and its effect on the final structure remain areas of active research. Some models suggest that the late stages are not perfectly spherical, with convective plumes and waves creating uneven structures that may later affect the collapse and explosion. Above the silicon burning layer lie the oxygen burning shell, the neon and magnesium region, the carbon and oxygen zone, and the helium-rich shell, possibly with little or no hydrogen remaining. Each of these layers contributes weight and pressure to the region below. The silicon burning layer must support all of this overlying mass, even as it is itself supported by reactions that are losing effectiveness. The balance becomes more delicate. If the energy from burning decreases or neutrino losses increase, the layer contracts, raising temperature and driving reactions faster. This feedback can maintain balance for a short time, but it also leads to rapid exhaustion of the fuel. The chemical direction of this layer is toward the iron group, a set of nuclei that includes iron, nickel, cobalt, and nearby elements. These nuclei are among the most tightly bound, meaning that fusing them into heavier elements does not release energy under normal stellar conditions. Instead, such fusion would require an input of energy. This marks a turning point in stellar evolution. As the core becomes dominated by iron group material, the star loses its ability to support itself through fusion at the center. The silicon burning layer is therefore the last stage where fusion can provide significant outward pressure. It prepares the core for the transition to an iron-rich state that cannot sustain further fusion support. The production of iron group elements in this layer does not immediately lead to collapse. The core can remain supported for a short time by pressure, including electron degeneracy pressure. However, the presence of iron group nuclei means that the path of energy generation has reached its limit. The star is now dependent on its remaining pressure sources rather than on fresh fusion energy in the core. As silicon burning proceeds and fuel is exhausted, the inner core grows in mass and becomes more dominated by iron group material. The boundary between the silicon burning region and the inner core shifts as more material is processed. Neutrino emission becomes especially intense in this stage. Processes such as pair production, where high-energy photons create electron-positron pairs that later annihilate into neutrinos, and other weak interactions produce a flood of neutrinos that escape the star. This energy loss accelerates the contraction of the core and shortens the remaining time before collapse. The star is still stable in the sense that forces balance at each layer, but the balance is fleeting and increasingly dependent on conditions that are changing rapidly. The silicon burning layer is also sensitive to the star's earlier history. The mass of the core, the degree of rotation, the effects of any companion, and the pattern of previous mass loss all influence how much material reaches this stage and how it behaves. A more massive core may reach higher temperatures and densities more quickly, while a less massive one may evolve slightly differently. Rotation can introduce asymmetry and mixing. Though its exact influence on the silicon burning stage is complex and not fully determined in all cases, observations of supernova remnants and light curves provide indirect clues, but the detailed inner structure remains hidden until the moment of collapse and explosion. In this region, the star has reached the last steady furnace. Silicon and related nuclei are processed in a rapid, high-energy environment that builds iron group material. The layer supports the weight of the outer shells while losing energy to neutrinos and approaching the limits of fusion. Its existence is brief but decisive. It marks the end of the star's ability to rely on nuclear burning for long-term stability. The inward path has moved from the cold outer cloud to the hot, stripped surface, through layers of helium, carbon, oxygen, neon, and now silicon. Each step has brought the star closer to a state where pressure can no longer resist gravity through fusion. In the silicon burning layer, the final steady support is nearly spent, and the inner core prepares to become a region where fusion ceases to sustain the star. Inside the silicon burning layer, the inward path reaches the boundary of the iron core, where the star's usual source of support changes in a fundamental way. Iron in this setting refers to iron group material, including iron, nickel, cobalt, and nearby nuclei that are tightly bound. These nuclei form after silicon burning has driven matter toward the most stable arrangements available through ordinary stellar fusion. The iron core is not made only of one isotope or one pure element, but it is dominated by nuclei near iron in binding energy. It sits at the center as the innermost ash of the star's long sequence of burning stages. Above it, shells may still burn, but at the core boundary the central material has reached a state where fusion can no longer provide useful outward support. The importance of iron comes from nuclear binding energy. In lighter elements, fusion can release energy because the combined nucleus is more tightly bound than the nuclei that joined to make it. This released energy becomes heat and pressure that help resist gravity. For iron group nuclei, the situation changes. They are already so tightly bound that fusing them into heavier nuclei does not release energy under normal stellar conditions. Instead, it requires energy. The core therefore cannot start another stable burning stage that supports the star in the same way hydrogen, helium, carbon, oxygen, and silicon did. It is ash in the deepest sense, not because it is cool, but because it is the end product of energy-releasing fusion. The iron core boundary is not a solid wall, it is a transition region in dense plasma, where composition changes from silicon-rich material outside to iron group material inside. The boundary may shift as silicon shell burning adds more iron group ash to the core. With each addition, the iron core grows in mass. The material inside is extremely hot and dense, but heat alone cannot solve the problem. Without a new energy source from fusion, the core depends on pressure already present in the matter. A major part of that support comes from electrons packed closely together. Electron degeneracy pressure resists compression because quantum rules prevent electrons from all occupying the same low-energy states. This pressure can support the core for a time, but it has limits. As the core gains mass, gravity strengthens, more material presses inward, and the electrons must support more weight. The core approaches a critical condition related to the maximum mass that electron degeneracy pressure can hold against gravity. This limit is often discussed through the Chandrasekhar mass, which is about 1.4 times the mass of the Sun for an ideal cold white dwarf made of certain material. In a massive star's hot iron core, the exact condition is more complex because temperature, composition, entropy, and electron captures matter. Still, the broad meaning remains clear. There is a limit to how much mass electron pressure can support. As the iron core grows toward that limit, the balance becomes unstable. The core is also losing energy through neutrinos. In these late stages, neutrinos escape easily from the dense interior, carrying energy away without pushing outward in the same way trapped light does. This loss reduces thermal support and encourages further contraction. As contraction proceeds, temperature rises, but the rising temperature cannot start a new helpful fusion stage in the iron core. Instead, high-energy photons begin to harm the support. They can break iron group nuclei into lighter particles, a process called photodisintegration. This process consumes energy rather than releasing it. Energy that might have helped maintain pressure is used to pull nuclei apart. The core becomes more vulnerable as its own heat begins to undo the nuclei that mark the end of fusion. Another process weakens the core through electron capture. Under extreme density, electrons are forced into protons in atomic nuclei, turning protons into neutrons and releasing neutrinos. This reduces the number of free electrons available to provide degeneracy pressure. It also lets more neutrinos escape, carrying away energy. The core therefore loses support in two connected ways. Pressure drops because there are fewer electrons, and energy leaves through neutrinos. Electron capture becomes increasingly important as density rises. It changes the composition of the core, making it more neutron-rich, and it helps push the star from temporary balance into rapid collapse. At the iron core boundary, the surrounding layers still matter. Silicon burning may continue just outside, feeding ash inward, oxygen, neon, carbon, helium, and any remaining outer material pressed down through their weight. The core cannot ignore the star around it. Every shell above contributes to the gravitational burden, yet the boundary itself is where the central failure begins to be defined. Outside, some nuclear burning can still release energy. Inside, the iron group material cannot do so. The star now contains a center that is hot, dense, and unsupported by further fuel. The boundary is therefore not only a chemical transition, it is a physical threshold between material that can still burn for support and material that cannot. The size of the iron core depends on the star's earlier life. A more massive evolved core can build a larger iron core. Rotation, mixing, mass loss, and binary interaction can alter how much material reaches the center and how shells add to it. The exact core mass before collapse is one of the crucial results of stellar evolution models. It affects whether the collapse produces a neutron star or a black hole, how much material falls back, and how much energy can be carried outward. In the most massive strip stars associated with hypernovae, the core may be large, and the later outcome may involve black hole formation. But at this boundary, the immediate focus remains the same for all core collapse paths the iron-rich center has reached the end of energy-producing fusion. The core is sometimes described as inert, but this word needs care. It does not mean inactive or cold. The iron core is intensely hot, dense, and filled with reactions that change nuclei and particles. It is inert only in the sense that ordinary fusion of its main nuclei cannot release energy to support the star. The matter inside is in motion at microscopic scales. Electrons are squeezed into high-energy states. Nuclei interact with electrons and photons. Neutrinos stream away. The core is active in its transformations, but none of these transformations restore stable pressure for long. Instead, they remove support or consume energy. The boundary may also carry the imprint of uneven late burning. Silicon shell burning outside the core can be convective and may not add material in a perfectly smooth way. The star is often modelled in one dimension for many studies, but real stars are three-dimensional. Motions in the late shells can make small differences in density and composition. These differences may become important later when collapse and shock formation occur. It remains uncertain exactly how all such pre-collapse structure appears in each real star. Observations after explosions and detailed simulations help narrow the possibilities, but the living iron core remains hidden until the star's final moments. The iron core grows quietly by astronomical standards. It is not visible from the surface as a separate object. A distant observer may still see a hot stripped star with strong winds or a luminous evolved massive star. The outer light does not announce each change at the center. Deep inside, however, the core approaches the point where pressure can no longer hold. Silicon burning adds mass. Neutrinos drain energy. Electron captures reduce electron pressure. Photodisintegration waits at the highest temperatures to consume energy. Each process moves the core away from stable support. In this inward region, balance comes undone without outward drama at first. The star has reached the iron core boundary, where the long chain of fusion has ended in tightly bound nuclei. The surrounding layers still press inward. The core still holds for a short time through pressure, especially electron degeneracy pressure, but the support is being weakened by the very conditions created by gravity. There is no new fuel stage beneath iron to restore the old pattern. The center becomes a dense, hot, iron group mass at the edge of instability. The path inward now rests at the threshold where the star's deepest material can no longer earn its support by burning, and the next change belongs to gravity itself. Inside the iron core boundary, the star enters core collapse, the inward fall of its central material under gravity. The region is now the iron-rich core itself, no longer supported by energy-producing fusion. For a brief time, pressure from packed electrons and hot matter resists the inward pull. Then the balance fails. The core has grown too massive and too dense for its existing support to hold. Electron captures remove electrons that once helped provide pressure. Neutrinos carry away energy. High-energy photons begin to break apart ion group nuclei, consuming heat that had helped maintain resistance. These processes do not push the core outward. They take away the supports that kept gravity in check. The center begins to fall inward. The collapse is rapid because gravity acts on every part of the core at once. The inner material accelerates toward the center, and the density rises sharply. The core does not fall like a rigid object. Different parts move at different speeds. The inner core, the deepest part, collapses almost together, while the outer core falls inward from above. Matter that had been a dense plasma becomes more compressed with each moment. Electrons continue to be forced into protons, making more neutrons and releasing more neutrinos. The core becomes increasingly neutron-rich. The number of particles able to provide electron pressure drops, and gravity becomes still more dominant. The change is not a slow, aging process now. It is a dynamical collapse, meaning motion itself becomes the defining state. As density increases, the distances between nuclei shrink. Matter moves from the conditions of an extremely dense stellar core toward the conditions found inside atomic nuclei. At first, the material still contains nuclei and free particles. As compression grows stronger, nuclei are pushed so close that ordinary descriptions of separate atoms no longer apply. The gas is not made of atoms in the usual sense. It is a hot mixture of nuclei, nucleons, electrons, photons, and neutrinos, where nucleons means protons and neutrons. Electron capture continues, turning more protons into neutrons. The escaping neutrinos carry away information and energy, though at the highest densities even neutrinos begin to interact more often and become partly trapped for a short time. The inner collapse releases gravitational energy. Gravity does work as matter falls inward, and the amount of energy involved is enormous. Much of it becomes internal energy in dense matter and neutrinos. Only a small fraction, if it reaches the outer layers, is needed to power a visible stellar explosion. In the collapsing core itself, however, the energy is not a bright outward flash. It is locked into compression, particle reactions, and neutrino production. The surface of the star remains far away in terms of density and optical depth. Light cannot carry a warning from the center fast enough to change the outward appearance before the inner event has already advanced. The collapse continues until the central density approaches nuclear density, the density found inside atomic nuclei. At this point, the behavior of matter changes. The strong nuclear force and neutron degeneracy pressure become important. Neutron degeneracy pressure is the resistance of tightly packed neutrons to being compressed into the same quantum states. The inner core stiffens because matter becomes much harder to squeeze further. This stiffening does not mean the whole star is saved. It means the innermost falling material can slow abruptly. The inner core reaches a minimum size and rebounds slightly as the equation of state, which describes how pressure responds to density and temperature, becomes much stiffer. The outer core is still falling when the inner core stiffens. This creates a sudden mismatch. The innermost matter has slowed and compressed into an extremely dense object, while overlying material continues to plunge inward at high speed. The collision between infalling material and the stiffened inner core helps form a pressure wave that steepens into a shock wave. A shock wave is a moving front where pressure, density, and temperature change abruptly. In ordinary description, it may sound like an explosion, but at this inner stage the shock is born deep inside the star and immediately faces heavy resistance. It must push through dense infalling matter and through layers that can drain its energy. The first shock loses energy quickly. One major loss comes from photodisintegration, As the shock moves outward through iron-rich material, it heats nuclei and breaks them into lighter particles, especially protons and neutrons. This consumes energy. Another loss comes from neutrinos, which continue to be produced in great numbers. The shock can stall, meaning it slows and becomes a standing or weakened shock rather than racing outward immediately. In many core collapse models, a successful explosion requires additional energy deposition, especially from neutrinos heating material behind the stalled shock. The exact mechanism is complex and remains an active area of research, with rotation, magnetic fields, turbulence, and asymmetry all able to matter. In this section's region, the core collapse itself has created the conditions, but the outward blast is not yet the focus. The collapsing core is also divided by communication limits. During the rapid fall, pressure signals cannot travel across the entire core fast enough to keep all layers moving together. The inner core collapses nearly homologously, meaning velocity is roughly proportional to radius, while outer parts fall more freely. This structure affects where the bounce occurs and how the shock forms. The mass of the inner core at bounce depends on entropy, electron fraction, and the nuclear equation of state. Electron fraction means the number of electrons compared with the number of baryons, where baryons are particles such as protons and neutrons. A lower electron fraction reduces electron pressure and changes the collapse. These details are technical, but their plain meaning is that the core's composition and heat decide how it falls. Neutrinos become central in this region, even though they're nearly invisible. As density rises, electron captures make a burst of electron neutrinos. At lower density, they stream outward easily. At higher density, the core becomes opaque even to neutrinos for a short time, so they diffuse outward more slowly from deep regions. When the shock passes through certain layers, a sharp neutrino signal can be produced. Detectors on Earth have observed neutrinos from a nearby supernova in the Large Magellanic Cloud, confirming that core collapse releases most of its energy in neutrinos. For a hypernova-forming star, the neutrino physics remains part of the core event, though the final energy and shape may require additional effects such as rapid rotation and magnetic fields. The collapse also changes the meaning of time inside the star. Earlier burning stages could be measured in years, days, or longer intervals. Core collapse unfolds in seconds. The inner core falls, reaches nuclear density, stiffens, and launches a shock over a very short time. The outer stellar layers do not yet know the full change in a visible way. The central event is hidden behind immense optical thickness. Gravity, particle physics, and nuclear forces now set the pace. The star has moved beyond the slow adjustment of burning shells into a regime where matter rushes inward, and support is rebuilt only in the form of an ultra-dense central object. Whether the central object remains a neutron star or continues toward a black hole depends on mass, energy, rotation, and how much material later falls back. At the instant of core collapse, the forming object is often described as a proto-neutron star, a hot, newly formed neutron-rich core. It is not yet a settled neutron star. It is swollen by heat, rich in trapped neutrinos, and still receiving in falling matter. If it gains too much mass, pressure may not support it permanently. In the most massive cases, collapse can continue into a black hole. At the present region, the important point is the formation of an extremely dense center from the fallen iron core. Core collapse is the inward failure that turns the massive star from a layered furnace into a compact remnant in formation. The iron-rich material can no longer burn for support. Electron captures reduce pressure. Photodisintegration consumes energy. neutrinos carry energy away. Gravity pulls the central matter inward until nuclear forces stiffen the deepest region, and a shock is born against the continuing fall. The process remains hidden from the surface while it happens, but it defines the star's fate from the inside. Matter rushes inward, not as a symbol of destruction, but as the direct consequence of a core that has reached the end of fusion support and must answer to gravity. Around the collapse center, the next region is the place where the first shock, rotation, magnetic fields, and narrow outflows may begin to shape the event. This is not the broad outer explosion yet. It is the deep engine region just outside the forming compact object, where matter is still falling inward while some energy tries to move outward. In an ordinary core collapse supernova, the stalled shock may be revived mainly through neutrino heating and turbulent motion. In the most energetic stripped explosions called hypernovae, observations and models often point to an additional engine, especially when the event is linked with a long gamma-ray burst. That engine is thought to involve rapid rotation and, in some cases, the formation of a black hole or a highly magnetized neutron star. The exact path can vary, and not every hypernova requires the same details. The shock formed at core bounce first moves into dense material above the compact center. It loses energy as it breaks heavy nuclei apart and as neutrinos carry energy away. The shock may slow and stall, becoming a boundary between infalling matter outside and heated, disturbed matter inside. Behind this shock, neutrinos stream from the hot proto-neutron star or from matter near the compact center. Some neutrinos are absorbed by nearby gas, adding heat. This heating can help push material outward if it overcomes the weight of continuing infall. Turbulence, meaning irregular motion in the gas, can increase the time matter spends in the heating region. The combination can revive the shock in many models of core collapse explosions, although exact details remain an active research topic. For a hypernova, the energy scale is unusually large. Observed hypernovae show broad spectral lines, which indicate very fast ejecta, and their total kinetic energy can exceed that of many ordinary core collapse supernova. A compact stripped star makes it easier for high-speed material from deep regions to escape without being slowed by a large hydrogen envelope. Still, high energy requires a strong power source. One proposed source is the rotational energy of a newly formed black hole surrounded by an accretion disk. An accretion disk is a rotating flow of material spiraling around a compact object. Another proposed source is a rapidly rotating neutron star with an extremely strong magnetic field, often called a magnetaire. Both can, under the right conditions, inject energy into the surrounding star. Rotation is central because it can organize the collapse. If the core keeps enough angular momentum, not all matter falls directly inward. Some material forms a disk or thick torus around the compact object. In a black hole engine model, gas in the disk heats strongly as it spirals inward. Magnetic fields can be wound and amplified by rotation. Energy may be extracted from the spinning black hole or from the disk, helping to drive narrow jets along the rotation axis. A jet is a focused outflow of matter and energy, moving through a limited direction rather than evenly in all directions. In this deep region, the jet begins as a narrow channel trying to push through falling stellar material. A magnetar engine is different but shares the importance of rotation and magnetic fields. A neutron star only a few tens of kilometers across can rotate many times each second if the collapsing core had enough angular momentum. If its magnetic field is extremely strong, the rotating field can transfer energy to surrounding matter. This can inflate a hot bubble and help drive an energetic explosion. In some models, it may also help form collimated outflows, meaning outflows narrowed into preferred directions. A magnetar can lose rotational energy over seconds to longer times, depending on its field strength and spin. This energy can brighten and accelerate the explosion. It remains uncertain which observed events are powered mainly by black hole engines and which by magnetars, and some events may involve overlapping effects. Magnetic fields begin as fields inside the progenitor star and are amplified during collapse. Compression strengthens them, and rotation can wind them into stronger toroidal fields, meaning fields wrapped around the rotation axis. Turbulent motion and instabilities can increase them further. Strong magnetic pressure can then push against the surrounding plasma. If the field is organized enough, it can help drive material outward along the poles, where resistance may be lower than near the equator. This does not mean the star has an empty tunnel waiting for the jet. The jet must drill through dense stellar matter. It can be slowed, disrupted, or choked if it fails to reach the surface. When it succeeds in some stripped stars, it may later be associated with high energy emission. The deep engine region is therefore strongly asymmetric. The earlier layers of the star may have been described as shells, but collapse and rotation break the simplicity of perfect spheres. Along the rotation axis, a jet or polar outflow may carry energy outward. Around the equator, matter may continue to fall inward or form a disk. Between these regions, heated gas moves in plumes and turbulent flows. The explosion can begin stronger in some directions than in others. Observations of hypernovae and gamma-ray burst supernovae often suggest a symmetry through broad lines, polarization, and the distribution of elements in remnants. These clues support the idea that some energetic explosions are not evenly spherical. The material near the forming compact object is transformed by heat and particles. Nuclei may be broken apart into free protons and neutrons. Neutrinos interact with this matter and can change the balance of protons and neutrons. Some outflows from disks may create new elements, depending on their neutron richness, entropy, and expansion speed. The details are complex and remain uncertain in many models. At this inner stage, the important idea is that the engine region is not only mechanical, it is also nuclear and particle-rich, with neutrinos, magnetic fields, and hot matter all shaping the flow. The jet, when present, is not the whole explosion at first. It is a channel of energy moving through the inner star. As it pushes outward, it drives shocks into surrounding material and deposits energy sideways as well as forward. A cocoon of hot shocked gas can form around it. This cocoon may help unbind parts of the star and contribute to the broad hypernova ejector. If the jet is powerful and the star is compact enough, it may break out of the stellar surface. If it fails, it can still deposit energy inside and produce an energetic asymmetric explosion without a visible gamma-ray burst. This difference helps explain why not all broad-lined energetic supernovae are observed with gamma-ray bursts. The deep shock and jet formation region is controlled by times measured in seconds. Matter falls inward rapidly. Neutrinos stream and diffuse. Magnetic fields wind. A disk may form. A jet may start, strengthen, weaken, or stall. The outer layers are still nearby in mass, but not yet the main region of description. The drama here is inward and central, determined by compact object physics and the star's rotation. Observations cannot see this engine directly while it is buried. Scientists infer it from the later explosion energy, shape, light, spectra, and high-energy radiation when present. In this region, force finds a path through matter that is still collapsing. The first shock alone may not carry enough energy for a hypernova, so rotation, magnetic fields, accretion, or a magnetar may add power. Narrow outflows can begin near the compact center and push into the inner layers. While neutrinos and turbulent heating continue to influence the shock, it remains uncertain which engine operates in every case, but the common feature is a deep source of energy beyond steady fusion. The star has passed from inward fall to the first organized outward motion, where the path of the explosion is shaped close to the remnant that is forming at the center. Beyond the deep engine region, the hypernova ejecta form the next outward layer, where energy delivered from the center begins to drive the star's material outward at high speed. This region includes the layers that were once the oxygen, neon, carbon, helium, and any remaining outer material, now responding to a powerful push from within. The ejecta are not a thin shell at first. They are a broad, expanding mass of gas with a wide range of speeds, densities, and compositions. The inner parts are heated and accelerated by the energy source near the center, while outer parts are swept up and carried along. The motion becomes outward rather than inward, marking the transition from collapse to explosion in the surrounding star. The energy that powers this expansion comes from the collapse and from the engine described in the deeper region. A portion of gravitational energy released during collapse is transferred to the surrounding matter. Additional energy may come from neutrino heating, from rotation and magnetic fields, from an accretion disk around a forming black hole, or from a rapidly rotating magnetar. The exact combination remains uncertain in detail for each observed event, but the result is clear. The star's layers receive enough energy to overcome gravitational binding, allowing them to move outward and escape. In a hypernova, this energy is especially large, leading to unusually high velocities in the ejecta. The velocities in this region can reach tens of thousands of kilometers per second in the fastest parts. This speed is inferred from the broadening of spectral lines, where the range of velocities in the expanding gas spreads the light over a wide range of wavelengths. The faster the gas moves, the broader the lines appear. Hypernovae often show very broad lines, indicating that a large amount of mass is moving at high speed. The expansion is not uniform. Some regions may move faster than others, especially if the explosion is asymmetric. Jets or polar outflows can create faster channels, while equatorial regions may expand more slowly. The ejecta therefore carry a memory of the inner engine's geometry. As the ejecta expand, they cool. Cooling does not mean they become cold in an everyday sense, but their temperature drops as energy spreads through a larger volume. At the same time, radioactive isotopes produced in the inner layers begin to decay. Nickel-56, created during silicon burning and possibly during the explosion itself, decays into cobalt and then into iron. Each decay step releases energy in the form of gamma rays and particles. This energy is deposited into the expanding gas, heating it and powering the visible light of the supernova. In hypernovae, the amount of nickel can be large, contributing to a bright and energetic light curve. The composition of the ejecta reflects the layered structure of the star before collapse, but it is altered by mixing and by explosive burning. Inner layers rich in iron group elements may be carried outward. Oxygen, silicon, sulfur, calcium, and other elements appear in different regions depending on how the explosion moved through the star. Mixing can bring deeper material closer to the surface of the ejecta. This mixing is often needed to explain observed spectra, where elements from different layers appear together. The exact degree of mixing depends on instabilities during the explosion, such as Rayleigh-Taylor instabilities, which occur when a denser fluid pushes into a less dense one under acceleration. These instabilities can create finger-like structures that mix material across layers. The ejecta interact with any material that was lost from the star before the explosion. Earlier winds and shells from the stripping phases may surround the star at various distances. When the fast ejecta collide with this circumstellar material, shocks form. These shocks heat the gas and can produce additional radiation at different wavelengths, including radio and X-ray emission. The strength of this interaction depends on the density and distribution of the surrounding material. In some cases, interaction is weak and the ejecta expand mostly into a low-density environment. In others, strong interaction can shape the light curve and spectral features. The expansion also carries angular structure from the inner engine. If jets were present, the ejecta may be faster and more energetic along certain directions. This can lead to anisotropic expansion, where properties vary with direction. Observations of polarization in some supernovae suggest that the photosphere, the effective visible surface of the expanding ejecta, is not perfectly spherical. The shape may be elongated or otherwise distorted. This supports the idea that the explosion is not always symmetric. In hypernova associated with gamma-ray bursts, the alignment of the jet with the observer's line of sight plays a crucial role in whether high-energy emission is detected. As the ejecta move outward, they become more transparent. Early on, the dense gas traps radiation, and energy is diffused outward slowly. As the density drops, photons can escape more easily. The observed light curve rises to a peak and then declines as the radioactive energy source diminishes and the ejecta continue to expand. The timing and brightness of this light curve provide information about the mass of the ejecta, the amount of radioactive material, and the energy of the explosion. Hypernovae often have broad light curves, indicating large ejecta masses and high energies. The outermost parts of the ejecta may include material that was originally near the star's surface before collapse. In a stripped star, this may be helium, or even deeper material if the stripping was extensive. Hydrogen is often weak or absent in hypernova spectra. Consistent with earlier loss of the hydrogen envelope, helium may or may not be visible, depending on excitation conditions and mixing. Oxygen is often strong, reflecting the large oxygen-rich zones in massive stars. The spectral evolution over time shows how different layers become visible as the ejecta expand and thin. The ejecta also carry momentum and energy into the surrounding interstellar medium. Over time, they will sweep up ambient gas, slow down, and form a supernova remnant. In the early hypernova phase, however, the ejecta are still dominated by their initial expansion. The energy distribution among different layers and directions continues to evolve as shocks propagate and as internal pressure gradients drive motion. The region remains dynamic, with density and temperature changing as the expansion proceeds. Uncertainties remain in the detailed modelling of hypernova ejecta. The exact mechanism of energy injection, the role of jets, the degree of mixing, and the interaction with circumstellar material all influence the outcome. Observations across many wavelengths, combined with theoretical models, help constrain these factors, but each event can show unique features. Despite these uncertainties, the general picture is well established. A powerful energy source drives the star's layers outward at high speed, producing broad spectral lines, large kinetic energy, and, in some cases, associated high-energy emission. In this outward-moving region, the star's material is no longer bound to the center. It is expanding into space, carrying with it the elements forged during the star's life and final moments. The ejecta are the visible body of the hypernova, shaped by inner processes and now interacting with the wider environment. The calm inward layering has given way to a rapid outward flow. Matter that once formed a stable sequence of shells is now part of an expanding cloud. its motion and composition revealing the depth and energy of the processes that occurred at the star's core. Outside the main body of the expanding hypernova ejecta, the next region is the narrow path through which high-energy radiation may escape when the central engine creates a successful relativistic jet. Relativistic means moving at a speed close enough to the speed of light that the effects of Einstein's relativity become important. In some stripped massive stars, the collapsing engine produces a jet that drills through the star and breaks out beyond the surface. When this happens, a beam of gamma rays may be released along the jet's direction. Gamma rays are the highest energy form of light. The event is then observed as a long gamma ray burst if the beam points near Earth, and if the jet remains powerful enough to produce detectable radiation. The gamma ray burst region is not a wide glowing sphere around the star, it is strongly directional. The energy is concentrated into two opposite beams along the rotation axis in many models. Although the details may vary, this beaming is important because it means many such events may occur without being seen as gamma ray bursts from Earth. If the beam points elsewhere, observers may see the hypernova without the high-energy burst, or they may see only later afterglow emission if conditions allow. The apparent brightness of a gamma-ray burst can be enormous because the energy is focused into a narrow angle. The true energy, corrected for beaming, is lower than it would appear if the emission was spread evenly in all directions, but it is still extreme by stellar standards. The jet must first pass through the star before the gamma-ray emission can escape freely. While it is inside the star, it pushes against dense material and forms a hot cocoon around itself. If the jet has enough power and lasts long enough, its head reaches the surface and breaks out. If it fails, the jet is choked and deposits its energy inside the star instead. A choked jet may still help power an energetic explosion, but it does not produce the same bright gamma-ray burst. The difference depends on the engine duration, the jet luminosity, the star's size, and the density of the layers it must cross. Compact strip stars are more favourable for successful breakout because the jet has less distance and less extended hydrogen-rich material to cross. After breakout, the jet expands into the space around the star. The gamma rays are thought to arise from energy dissipation within the outflow or from interactions between the outflow and its surroundings. Several mechanisms have been studied, including internal shocks, magnetic reconnection, and photospheric emission from the relativistic flow. Internal shocks occur when faster parts of the jet catch slower parts and convert some motion into radiation. Magnetic reconnection occurs when magnetic field lines rearrange and release energy. Photospheric emission occurs near the region where the outflow becomes transparent to its own radiation. Observations show rapid variability in gamma-ray bursts, which indicates that the emitting region is compact and powered by a central engine that changes over short times. The prompt gamma-ray emission, meaning the first bright high-energy phase, often lasts seconds to minutes for long gamma-ray bursts. Long bursts are the class associated with the collapse of massive stars, especially in star-forming galaxies. The duration is not the same as the full hypernova. The optical supernova light develops over days as radioactive energy diffuses through the expanding ejecta. The gamma-ray burst comes from the relativistic outflow and reaches distant space quickly. It is a separate region and timescale from the slower, wider ejecta. Both are connected to the same central collapsing engine, but they show different parts of the event. The radiation is strongly affected by motion close to the speed of light. Relativistic beaming concentrates light in the direction of travel. Time intervals appear shortened, and photon energies are shifted for observers along the beam. This is why a jet with a narrow opening angle can be visible across billions of light-years when aligned with Earth. The outflow must achieve very high Lorentz factors, where the Lorentz factor measures how strongly relativistic the motion is. In long gamma-ray bursts, this factor may reach tens to hundreds. Such motion requires the jet to carry a large amount of energy while remaining relatively clean of ordinary baryonic matter. Too much baryonic mass would make it difficult to accelerate the flow to the required speed. Around the jet, the surrounding material affects the later afterglow. Afterglow is emission that follows the prompt burst as the relativistic outflow slows down by sweeping up external gas. This interaction creates shocks that accelerate particles and amplify magnetic fields. The particles radiate across the electromagnetic spectrum, from X-rays to visible light to radio waves. The afterglow can last hours, days, weeks, or longer, fading as the blast wave expands and loses energy. The shape of the afterglow light curve can reveal the density of the surrounding medium, the jet opening angle, and the energy of the outflow. A steepening in the light curve, called a jet break, can indicate that the observer begins to see the edge of the narrow jet as it slows. The gamma-ray burst region also provides information about the star's environment. Long gamma-ray bursts are found in galaxies where massive stars are forming, because the progenitor stars live short lives and die near their birthplaces. Many occur in lower metallicity environments, although the relationship is not absolute. Lower metallicity can reduce wind mass loss, helping a massive star keep more angular momentum until collapse. Angular momentum is important for forming an accretion disk or rapidly rotating compact object. However, observations show diversity, and metallicity alone does not determine the outcome. The presence of a burst indicates that the star had the right combination of stripping, core rotation, compactness, and engine activity. The high-energy beam carries only part of the event's story. The wider hypernova ejecta carry most of the visible supernova material, while the gamma-ray burst reveals the fastest and most focused channel. In some well-observed cases, a broad-lined Type 1 C supernova appears with a long gamma-ray burst. Type 1c means the observed supernova spectrum lacks clear hydrogen and helium lines, showing that the progenitor had been stripped deeply before collapse. The broad lines show high velocities. This association supports the link between stripped massive stars, energetic explosions, and relativistic jets. Yet there are broad-lined type IC supernovae without detected gamma-ray bursts, showing that the jet may be absent, weak, choked, or pointed away. The region of gamma-ray emission is far from the dense core compared with the engine, but it's still close in cosmic terms. It forms along the path cleared by the jet, beyond the surface of the star and into the immediate surroundings. The radiation crosses space at the speed of light, reaching observers before the slower optical supernova becomes bright. Satellites detect the gamma rays first, then telescopes search for afterglows and the rising supernova light. In this way, the high-energy region acts as an early signal from the collapse of a massive star. Although it is visible only from favorable directions, uncertainties remain in the exact radiation mechanism of prompt gamma-ray bursts. Different bursts show different spectra, variability, and polarization. Some appear more magnetically dominated, while others can be explained with shocks or photospheric components. The central engine may be a black hole with an accretion disk in some cases, and a magnetar in others. Observations indicate the overall connection between long bursts and massive star collapse. But the detailed path from engine to gamma rays remains an active field of study. The known features are the narrow relativistic outflow, the high-energy light, the afterglow from external interaction, and the association with stripped energetic explosions. In this region, light crosses distance with unusual focus. A narrow jet escapes the dying star, and if it points toward Earth, gamma rays arrive as a brief, intense signal from a collapse that occurred far away. Around the beam, the wider hypernova continues to expand more slowly. The gamma ray burst does not replace the explosion. It reveals the fastest and most directed part of it. The path remains outer to inner in origin, but now follows the escape channel into space, where radiation from the jet leaves the star behind and travels through the surrounding medium. The beam carries evidence of rotation, compactness, and deep engine power, written in high-energy light that moves outward long before the full debris cloud fades. Beyond the initial burst and the fastest outflows, the expanding remnant becomes the next region, where the hypernova's debris cloud grows, cools, and interacts with the surrounding interstellar medium. This region develops over years to centuries after the explosion, though its early form begins immediately as the ejecta move outward. The remnant is not a static cloud. It is an evolving structure shaped by expansion, collisions, radiation, and the gradual mixing of stellar material with the gas between stars. The energy released during the hypernova continues to influence this region, long after the central engine has ceased its active phase. At first, the ejecta expand freely into the surrounding space. This phase is called free expansion because the mass of the swept-up external gas is small compared with the mass of the ejecta. The outer layers move outward at high speed, while inner layers follow behind. Density decreases as the volume increases, and temperature falls accordingly. The debris is still extremely hot in absolute terms, but it cools compared with its initial state. Radiation from radioactive decay continues to heat the inner regions for a time, but as the isotopes decay away, this internal energy source weakens. The remnant begins to rely more on kinetic energy, the energy of motion, than on internal heating. As the ejecta encounter the surrounding interstellar medium, a shock wave forms at the leading edge. This forward shock compresses and heats the ambient gas, raising it to high temperatures that can emit X-rays. At the same time, a reverse shock moves inward through the ejecta, heating the stellar material itself. The reverse shock is called reverse because it travels back toward the center in the frame of the expanding material, even though the entire system continues to grow outward. These shocks are important because they convert kinetic energy into thermal energy and radiation. They also help shape the remnant structure, creating layers of hot, shocked gas and cooler regions. The composition of the remnant reflects the star's life and its explosive end. Oxygen-rich filaments, silicon-bearing knots, and iron-rich clumps can be observed in some young remnants. These structures are not always evenly distributed. Instabilities during the explosion and during the early expansion can create clumps and asymmetries. Material from deeper layers may be carried outward in plumes, while some outer material may be left behind or mixed inward. The remnant becomes a complex three-dimensional structure, with variations in density, temperature, and composition across different regions. Over time, the remnant enters a phase where the mass of swept-up interstellar gas becomes comparable to or greater than the mass of the original ejecta. This marks the transition from free expansion to a more decelerated stage. The forward shock slows as it encounters more material, and the remnant's radius grows more slowly. The temperature of the shocked gas remains high, but radiative cooling becomes more important in some regions. Cooling can lead to the formation of thin shells and denser structures, where gas loses energy and contracts locally. The overall shape may remain roughly spherical, or become elongated depending on the initial explosion geometry and the surrounding medium. The interaction with the interstellar medium also spreads the elements created in the star into the galaxy: carbon, oxygen, silicon, iron, and many other elements are carried outward and eventually mixed into the gas that may form new stars and planets. The hypernova therefore contributes to chemical enrichment, adding heavy elements to the galactic environment. These elements are essential for the formation of rocky planets and for the chemistry that can support life. In this sense, the remnant is not only a fading trace of a violent event, it is also a source of material for future generations of stars. Magnetic fields play a role in the remnant as well. The shocks can amplify magnetic fields in the surrounding gas. These fields can influence the motion of charged particles and contribute to the acceleration of cosmic rays, which are high-energy particles that travel through the galaxy. The exact processes of cosmic ray acceleration in supernova remnants are still studied, but shock waves are considered a primary site for such acceleration. The hypernova remnant, with its high energy and strong shocks, is a likely contributor to this process. The remnant's radiation changes over time. Early on, the emission may be dominated by optical light from radioactive decay and recombination of ions. As the remnant expands and shocks develop, X-ray and radio emission become more prominent. X-rays come from hot gas heated by shocks, while radio emission often arises from electrons spiraling in magnetic fields, a process called synchrotron radiation. Observations across these wavelengths provide a detailed picture of the remnant structure and evolution. Each wavelength reveals different aspects, from hot plasma to cooler gas to magnetic activity. The shape of the remnant can retain signs of the original explosion's asymmetry. If jets or directional outflows were present, the remnant may be elongated or show bilateral features. If the surrounding medium is uneven, with denser regions in some directions, the expansion will be slower there and faster elsewhere. The result is a remnant that reflects both its internal origin and its external environment over long timescales. These differences may become less pronounced as mixing and expansion continue, but early structures can persist for significant periods. In the center of the remnant, the compact object formed during collapse remains. It may be a neutron star or a black hole, depending on the mass and evolution. In some cases, a neutron star can be observed as a pulsar, emitting beams of radiation as it rotates. In other cases, the central object may be faint or undetectable, especially if it is a black hole without significant accretion. The remnant therefore surrounds a central remnant that carries the outcome of the collapse. Even as the outer material disperses, the remnant continues to evolve over thousands to tens of thousands of years. Eventually, it will merge with the surrounding interstellar medium, losing its distinct identity as a separate object. The shock waves weaken, the temperature drops, and the enriched material becomes part of the general galactic gas. This long-term evolution completes the outward journey from a single massive star to a distributed set of elements and energy within the galaxy. In this region, the aftermath of the hypernova unfolds slowly compared with the rapid collapse and explosion. The expanding remnant is a bridge between the star's final moments and the broader galactic environment. It carries the chemical products of nuclear burning, the kinetic energy of the explosion, and the structural imprint of asymmetries and interactions. The star that once existed as a layered object has become a spreading cloud, its material no longer bound to a central structure but moving outward, cooling and mixing with the space between stars. At the center of the expanding remnant, the final inward region is the compact outcome of collapse, where gravity holds the densest material left behind. In the most massive hypernova pathways, This central remnant can become a black hole. A black hole is a region where gravity is so strong that, inside a boundary called the event horizon, light cannot escape outward to distant space. The event horizon is not a solid surface. It is a boundary in space-time, marking the limit beyond which all future paths lead inward. The black hole does not glow from its own surface, because it has no surface in the ordinary stellar sense. It is known by its gravity and by the behavior of matter and light around it. The path to a black hole begins with the collapsed core. During the first moments of collapse, a hot proto-neutron star may form when nuclear density matter stiffens and resists further compression. If this object remains below the maximum mass that neutron-rich matter can support, it may settle into a neutron star. If it gains too much mass from continuing infall, or if the original core is already too massive, support fails again. Matter continues inward, and the central object collapses into a black hole. In a hypernova-producing star, fallback can also be important. Fallback means material that was initially pushed outward but does not escape permanently and later returns toward the center. This returning matter can add mass to the remnant and help form or grow a black hole. The maximum mass of a neutron star is not known with perfect precision because it depends on the equation of state of ultra-dense matter. The equation of state describes how pressure, density, and energy relate inside matter denser than an atomic nucleus. Observations of heavy neutron stars show that neutron star matter can support at least about 2 times the mass of the Sun. But the upper limit remains uncertain. If the collapsed remnant exceeds that limit, no known pressure from neutrons or nuclear forces can hold it in a stable neutron star form. The inward fall continues until an event horizon forms. From the outside, the remnant is then described by mass, spin, and electric charge, though astrophysical black holes are expected to have negligible net charge. Spin is especially important in many hypernova and gamma-ray burst models. If the collapsing core keeps enough angular momentum, the newborn black hole may rotate rapidly. A rotating black hole is described by a space-time geometry that differs from a non-rotating one. Around it, infalling matter with angular momentum cannot drop straight in from all directions. Instead, it may form an accretion disk. In the disk, gas orbits, heats, loses angular momentum, and gradually moves inward. The disk can be extremely hot and dense, filled with nuclei, free particles, radiation, and neutrinos. Magnetic fields threading the disk and black hole region may help extract rotational energy and drive jets. This process is one of the leading ideas for the engines of long gamma-ray bursts linked to some hypernovae. The black hole itself remains hidden behind the event horizon. Any matter crossing that boundary can no longer send light or signals back to the outside universe. To a distant observer, the visible activity comes from the material outside the horizon, not from inside it. An accretion disk can shine brightly if matter is present. Jets can carry energy away along the rotation axis if magnetic fields and rotation organize the flow. If little matter remains nearby, the black hole may become quiet, detectable only through its gravity. In a hypernova remnant, the central black hole may be difficult to observe directly once the bright explosion fades, especially if it is not actively accreting. The black hole's mass reflects the final balance between ejection and fallback. Some of the original core and inner layers may be expelled, some may fall back. A stronger explosion can unbind more material and leave a smaller remnant. A weaker or more asymmetric explosion may allow more matter to return. In a jet-driven event, material along the poles may escape more readily, while equatorial material may continue to fall inward. The result can be a black hole surrounded for a time by a disk or torus, with outflows carrying energy and newly processed material away. The exact mass is therefore not determined by the original star alone. It is set by the interaction between collapse, engine power, explosion geometry, and the structure of the star before death. Inside the event horizon, the known laws of physics point toward continued inward collapse, but the final state at the deepest center is not fully described by current theory. General relativity predicts a singularity, a region where density and curvature become infinite in the mathematical description. Physicists understand that this prediction signals the need for a theory that combines gravity with quantum physics. Observations cannot probe the inside of the event horizon directly. For the purpose of the stellar story, the important point is not a speculative picture of the center, it is the observable boundary and its consequences. Once an event horizon exists, the central mass no longer returns light, matter, or ordinary signals from within it. The formation of a black hole also changes the fate of nearby matter. Gas falling close to the horizon releases gravitational energy as it heats and spirals inward. Some of that energy can power outflows before the gas crosses the horizon. If the disk is dense and hot enough, neutrino emission may be strong. If magnetic fields are strong and organized, electromagnetic extraction of rotational energy may contribute. These processes happen outside the horizon, in the region where matter can still communicate with the surrounding star and remnant. They can influence the explosion even though the black hole itself is defined by what cannot escape from within. The compact remnant is small compared with every earlier region. The molecular cloud stretched across light years, the giant star extended across many solar radii, the inner shells filled a stellar core. The black hole's event horizon may span only tens of kilometers for a remnant of several solar masses, yet its gravity governs the center of the remnant. It represents the final inward concentration of mass after the star has lost its outer layers, burned through its fuels, collapsed its iron core, and thrown much of its body into space. The scale has narrowed from a galactic cloud to a boundary smaller than a city, while the mass remains greater than that of the Sun. A black hole outcome is not the only possible end for every energetic, massive star explosion. Some events may leave neutron stars, including magnetars, and observations of different supernovae show a range of compact remnants. For hypernovae connected with long gamma-ray bursts, black hole engines are a leading model, while magnetar engines are also considered in many cases. The evidence can come from light curves, spectra, afterglows, host environments, and theoretical consistency. It remains uncertain for many individual explosions which compact object was left behind. The script's inward path rests on the black hole outcome because it is one central route from a giant star to an extremely energetic collapse. In the final center, gravity holds what remains. The black hole is not an explosion but the compact end of collapse. Around it, ejecta expand, remnants cool, and enriched gas spreads into the galaxy. Near it, any surviving disk may fade as material is swallowed or expelled. Farther out, as the debris carries oxygen, carbon, silicon, iron, and other elements into space, the black hole itself remains as a quiet gravitational object, shaped by mass and spin, separated from the visible universe by the event horizon. The star's long inward journey ends at this boundary, where the processes of fusion, pressure, and outward light no longer define the center, and gravity becomes the lasting form of the remnant. Across the wide remnant, motion becomes slower and more diffuse. The bright force of the hypernova fades into a cooling cloud, and the cloud gives its material back to the space between stars. Oxygen, Carbon, silicon, iron, and many other elements drift outward in uneven streams and knots. Some remain hot for a long time. Some join colder gas and dust. Over many thousands of years, the shape of the remnant softens as it mixes with the surrounding medium. The event that began inside a massive star becomes part of the galaxy's quiet circulation. At the center, the black hole remains separate from the glowing debris. It has no shining surface and no ordinary edge of matter. Its event horizon marks the place where paths lead inward, and outside that boundary, space carries the record of what once happened. If nearby gas falls toward it, the gas may heat and shine before it disappears. If little gas remains close, the black hole becomes nearly silent, held in place by gravity and known only through its influence. The larger story settles into a simple sequence. A cold cloud gathers mass. A giant star forms, shines, loses its outer layers, and builds heavier elements in deeper shells. Its core reaches iron, loses support, and collapses. Energy moves outward through shock, wind, jet, or magnetic flow, and the star's body expands into space. Some material escapes, some falls back. The center becomes compact, and in this path it becomes a black hole. Nothing in the remnant returns the star to its earlier form. Its matter continues outward, joining future clouds and future stars. Its center remains inward, hidden by gravity. The hypernova becomes less a single moment and more a passage of matter from one state to another, from cloud to star, from star to collapse, from collapse to remnant, and from remnant back into the slow dark spaces of the galaxy.